Hey everybody, welcome to another Avalanche Developer Community Call. My name is Gabriel Cardona and I am a developer evangelist from Ava Labs. And I'm happy to be here today and very stoked to be joined as always by some amazing engineers from Ava Labs. We have Patrick O'Grady, Stephen Butoff, Aaron Bookwald, and Jay O'Nor. Hopefully I got everybody's names there correctly and didn't mispronounce anything. So thank you gentlemen for joining us. Lots to cover today. So we're going to be talking about Cortina 5, the Precompile-EVM, and then the new Postman collection for the Avalanche Network Runner. So per the usual, I'm going to pass the mic off to Pog so that he can talk about Cortina 5. Go for it, gentlemen.
Cool. Yeah, so I'll share the screen here and then actually pass it to Steven, who will take the lead on going over the first major parts here.
Let me see that. There we go. So I think we can see Cortina 5 now. Yeah, so I think the last time we talked, we mentioned that we were going to increase the cadence of some of the AvalancheGo releases. We've been pushing out. We pushed out Cortina 5, and we're also about to push out Cortina 6. So the reason that we increased the cadence is because we want to limit the amount of DB changes to one per release. And we have a number of DB changes set up for both some of the consensus optimizations that we want to perform, but also for warp message verification performance. So Cortina 5 was set up for some of the consensus optimizations. So this is introducing the height indexing primarily on the proposer VM for the X chain. We're going to have a similar change for the P chain. The P chain is going to be a little bit more nuanced because it also has to have the inner VM index the heights, whereas on the X chain, it was just the proposer VM, which is the Snowman++ mechanism, which has this additional kind of block wrapper. So that was the namesake of Cortina 5. Inside of this, we also shipped a couple other changes. So one of the big changes inside of this, that was kind of like subtly included, was we changed some of the warp message structure. So specifically, we removed the destination field of warp messages and replaced it with a network ID field. The reason that we added the network ID field was on the very specific case of the primary network's P chain. It always has a global chain ID of all zeros because chain IDs are typically generated from the transaction that creates them on the P chain, but the P chain obviously can't kind of recursively do that. So in order to just be very paranoid and correct, we introduced the network ID. So if the P chain ever sends a warp message, then that will be the unique identifier for the P chain. And then the destination chain is really just part of the message payload. There's no exact reason for it to be in the warp message. It's generally probably going to be used by most messages, but it's not required. So we felt like that should just be moved into the payload. So that was one change. That was the reason why we had to change the RPC chain version as well to include that change. Yeah, there were a couple other interesting changes. So we introduced the ability to specify tracing headers. So this actually unblocks the ability to configure your kind of like own local tracing setup, which is really useful for benchmarking stuff. I think Patrick, you probably use it pretty heavily in the HyperSDK, so kind of managed to unblock that flow. And then there were a couple other kind of smaller changes, but for the most part, we're doing these kind of like micro releases to just kind of get these database migrations through. So Cortina 6 is going to be focused a lot on these validator diff changes. So we've been playing around with these on Fuji and mainnet, and we're really excited about the performance that we're seeing. I think we see on mainnet, it's around a 60x performance improvement on generating the validator set. And there's a very simple benchmark that shows a straight 15x improvement of just the benchmark. So pretty excited about that as far as a performance perspective. There's a bunch of other changes in addition to this change that are going to go in for the warp stuff, but this is the only dB change. The other ones can kind of just filter in without too much fanfare. So really excited for that to go in, and we'll be continuing with.
Do you remember
Sorry,
what PR that is?
That PR is 1752. But it should be there somewhere. Sorry. But anyways, yeah, so we'll be continuing with these kind of like faster paced releases until I think 1.10.7. And after that, we'll probably get back to our normal cadence of every other week. But yeah, I think that's kind of primarily my thoughts on the AvalancheGo releases. I don't know if there's anything else you wanted to shout out, Patrick.
Yeah, I want to call out in particular this database change that Steven's been working on. So for people that aren't familiar, I guess maybe to reiterate the important part here is when we do a warp message validation, typically that warp message validation is attached to some proposer VM block. So we call this the block context, or the proposer VM header as the block context. And that context contains the p-chain height at which the basically the signature should be verified. And so if you, let's say, have a height that's, there's no way you're going to have height always that's right at the tip. So usually there's some hip at the height is some number of blocks back from the tip. Well, that means AvalancheGo, when it's verifying that signature, needs to actually do like reverse diffs to see what the current validator set, or like the validator set, would have been at that particular height. So it's extremely important that that particular mechanism is very fast. And the p-chain's legacy representation of this used this like linked DB thing, which we had added a long time ago to support databases that didn't have range iteration on them. So like typically a function of many of these like key value databases is you can provide some sort of key prefix and then iterate either forward or backwards, sometimes backwards, on that prefix. And so it turns out to do that, you have to, I'm going to digress here, but you need to like order the entries in the database to do that efficiently. And if you can remove that requirement, you can sometimes make a key value store much more performant. Well, we decided not to go down that path for a number of different reasons. And so this linked DB that was in here was there for no reason, because it assumed the database couldn't do any range iteration. So we removed that, as well as made the underlying structure, like the key mapping of how these things were laid out, more efficient. And that has resulted in a massive gain in performance. So I think on Steven's benchmark, it's about a 15x improvement for this sort of function, but could very well be larger in practice. So this will be very useful, I think, for people. And the benefit here as well is we don't actually need to do a full migration of everything that's in the database, which is nice. So instead, typically what the operation you're doing is, as I mentioned, take the current height and then go back to the header of the block you're validating. And so once you add this change, you're typically, as long as like the blocks you're validating don't have like really low p-chain heights, should almost always be within the migrated or like new data format tip. So, it should be, you should notice immediately in the world where you're validating a lot of warp messages, which is what will happen in the near future. So really important change. Going through a lot of review right now, though, because it is a very sensitive change as well, right? It determines how diffs are generated at the validator state. The other one that's really important to call out, as Steven mentioned as well, is this trace header. And so the reason why this is super useful is we use something called OpenTelemetry to monitor traces in this like kind of agnostic format. We also, and so up until now on the HyperSDK, we've had to use like this extension called Zipkin to like visualize the traces, which has been suboptimal. And we haven't actually had a great local option on AvalancheGo. Steven investigated and actually found a really cool open source tool called Uptrace. You guys want to check it out. And it basically is this awesome, almost like Datadog in a box that you can hook up to anything that is running OpenTelemetry. And so the only thing that it needed, though, was to provide tracing headers. And so Steven added that option, and now you can run this locally. So I'm going to remove all the Zipkin related tracing stuff from the HyperSDK and port all this just to use Uptrace. But if you want to run your own kind of Datadog in a box, we recommend checking it out. This cool open source tool. All right, I think that was it. I don't think there was anything particular in core ETH you wanted to call out in this release, right, Aaron?
Yeah, the main thing were the API handler crash fixes, but I don't think we want to talk about it too much on this call. It's just migrating some fixes and a couple things. They're pretty well documented on GitHub as well.
Cool. All right. Well, with that, then let's go right into the Precompile-EVM. So we invited Jay, who's another engineer on the protocol team, to join. He's been spending a lot of time on the precompile support within the EVM. And so I think, we wanted to hear his perspective on things, but now I'll turn it over to Aaron and Jay. So do you want me to I'll go right to the repo to start off, and then you can kind of tell me where you want to go from there.
Yeah, definitely.
Obviously introduce the Precompile-EVM and all of that stuff too, but
Yeah, hello everyone. So this work started with a major refactor on the subnet EVM for the precompiles. We tried to give the best experience to developers for the precompile development and generating them, maintaining them. So we started a big refactor on the subnet EVM it was around February with the v0410 release. So yeah, it introduced modules for precompiles, which can be used to just as a single package. We can develop precompiles in a single package without any modification to other places. So this gave us the perfect opportunity to use precompiles as a package. And then we kind of started to think, what if we can provide a way to create a precompile outside of the subnet EVM. So this would be like a single package using subnet EVM under the hood and without any subnet EVM codes around the place. So it will be like a massive cleanup because subnet EVM is has a massive code base, and it maintaining it as a fork can be like a very hard, cumbersome process, and it could be just easier to maintain a single package rather than maintaining the whole subnet EVM. So modules gave this opportunity, and we kind of expanded the plugin runner in the subnet EVM and exported it as a function, as a library, so that other repos can import it and run the subnet EVM runner as a code. So the Precompile-EVM depends on that. In the plugin package, there's a main.go that runs the subnet EVM. So the runner that runs the subnet EVM. So it just actually wraps the whole subnet EVM in a single line, and it runs the subnet EVM as if it is the subnet EVM itself. So, and with the precompile refactor, we kind of changed how we introduce precompiles to the subnet EVM itself. So we developed the modules and we registered them through an external register by importing the precompile packages in the subnet EVM. So this repo also does the same thing. If you can open the same plugin package, Patrick, there's a line that says if you import your precompile package here, it will just register automatically. And yeah, in the precompiles, we have an actual example precompile in the Precompile-EVM in the Hello World branch. So maybe we can take a look at there. Yeah, so that's the actual example. Hello World is an actual precompile registered to subnet EVM, and in the module in it, it's registered itself to the subnet EVM. In the contract code, we have in the module, in it registers to the module, the subnet EVM modules. So it's a complete different precompile from subnet EVM's own default precompiles. So yeah, this is like a massive cleanup in terms of like developer experience, and we kind of kept everything else same, like scripts and the Solidity environment, hard hat environment, to provide like seamless migration from subnet EVM to Precompile-EVM. So everything else is very much same with the subnet EVM tools. And yeah, we also introduced the precompile generator tool with this major factor on the subnet EVM. So it also works. And here we have put it as a script under scripts folder, general precompile as such. This directly runs the precompile generator tool from subnet EVM, so we don't have to like copy it around and fork it. So yeah, this runs the precompile generator stuff, and it basically you can write your own interface. You can look at the contracts, and there should be like a hello world salt file in the contracts. Patrick, can you
Sorry,
copy
one,
under contracts?
Yep.
Interfaces. This is an example. Yeah, this is the actual. So this is what you need to start with your precompile journey. You need to do is just define some functions there with their signatures, like their input types, output types, and you can also specify if it requires a access module, which is called allow list. So with this, you can start like you need to create ABI from this, and then you can just feed it into the precompile generator tool, and it will take care of all required file generation, along with some template code, along with some skeleton codes in the precompile package. So this is the Hello World package generated from this Hello World function contract. Sorry, and there are like few files in the package. These are all generated by the tool, so you don't have to worry about them. All you need to do is take a look at the README in the package, in the Hello generated package, and just follow the guidelines there, and then you will be like able to implement your own functionality for a precompile, set it to an address, and just start using it.
Very cool. I know that one of the big pain points early on was, people took the subnet EVM with their precompiles, and then we're trying to find ways to actually like add that in. And so to make this more interesting, if it couldn't already be, I did this a long time ago using something called Random Party. Which, let me just share my screen to talk about like how this now is super different. So this is the Random Party Precompile-EVM fork I had to do. So what this looked like before was, all right, fork the entire subnet EVM. So now you get all these packages and code. You have no idea how they work. And as you can see, I am 409 commits behind master. So if I was to incorporate those changes in, I would have to now merge in upstream the changes across what looks like 805 files. And so the feedback, as you may expect, was, can we not do that? And so the random party changes are actually very minimal and almost entirely, they actually use our very old format as well. So it doesn't even look like this anymore. but was really just 2 files. So I added 2 files, and then it ended up with me maintaining, a couple 100,000 lines of code. So with the Precompile-EVM, this is much more straightforward. And my usual gauge for like, is a product or like a project that we release useful, is to see like, if someone was to actually take it and do something to it, would they be able to with minimal help from us? And what was really cool was that this group ended up doing that very shortly after the release, I think within 24 hours, which was creating a Precompile-EVM that implemented the pasta curves, which is really cool. And so we tried to get the group on for this chat. They weren't able to make it today, but maybe Aaron and Jay, you want to cover a little bit about what this is and why you may want it?
Yeah, sure. Yeah, like Patrick said, the fact that we were able to see people doing something interesting with this in less than 24 hours, whereas before there was very little development of stateful precompiles and a lot of feedback that it was difficult to use, really shows that this makes it, 10 times easier to finally use. And in addition to this project as well, our developer relations team has also been experimenting a ton with this, building out different things, and the feedback has been incredibly positive on Precompile-EVM. And very much so of the flavor of like, I didn't know how to use it before. It's super easy now, which, that feedback is pretty direct. So it seems to have gotten a lot easier. It made life a lot easier for any types of devs that want to extend the EVM in any way. And then as for, what is interesting about Precompile-EVM, the pasta curves being integrated, we get a lot of people that are very interested in experimenting with different types of zero-knowledge cryptography on blockchains. And the problem for a lot of them is, if they're coming from maybe the Ethereum research community or an academic background, they really want to focus on primarily that. They want EVM compatibility because they want to use all of the existing tools that are already out there, and they want to experiment with this one particular thing. And the pasta curves, the Paulus and Vesta curves are particularly interesting. Right now, I think they're used in incrementally verifiable computation and being very popular in a number of different frameworks that are under active development. And in order to actually use them, these curves they don't exist as precompiles on Ethereum. And it's a very slow process to add new precompiles either to Ethereum or even to the Avalanche C chain, because there's a sort of a higher bar for, okay, we want to actually wait for these libraries to be fully mature. But the reason this is so interesting is that if we can make Avalanche one of the best places to experiment, then it very quickly becomes one of the best places to build as well. And so if we can make it extremely easy to add whatever cryptographic functionality people want, we can make Avalanche a really powerful place to build. And one of the issues with blockchains is as soon as you add some functionality, you're more or less committed to that almost forever. And as ZK tech moves forward so quickly, there's a huge amount of transition in what the popular curves to use are, what the most cutting edge technology is. And so it can become really, really difficult for an existing network to make a commitment to an individual cryptographic curve. And the ability to experiment, try things out, and throw things away quickly can be a really, really powerful notion. So the ability to take whatever curve, whatever latest tech exists, and throw it into the EVM extremely quickly, focusing on the cryptographic primitive and building something on top of that, is a really, really powerful notion that we were really, really happy to see some great teams already experimenting with. And from it just so happened that around the same time that we launched this, I would say personally, I think I talked to 5 different projects that were trying out using incrementally verifiable computation. It just so happened to come all around the same time that there was a flood of teams interested in working on this. So it was really great feedback that this actually made that an incredibly easy process to experiment.
I'm also pretty interested in networks that are more fluid with their precompiles. So like something like the C chain or like Ethereum mainnet, typically precompiles are kind of like add it and never remove it, never touch it. It's kind of like there. And there are some kind of like more famous examples, if you look back in the history of Ethereum, where like some precompiles have been added and there's like no usage at all, to a point that like I'm sure that if they were to remove it, people probably wouldn't care that much. But they're still kind of there. And even if they were to be removed, they would have to be kind of like maintained inside the client anyways, right? Like Generally, precompiles are deactivated. They're not removed because if you're reprocessing historical blocks, you still have to be able to actually perform that computation. But I have always been a huge proponent of networks that don't necessarily require their validators to support historical execution of blocks, which would actually mean that the lifecycle of the code can mirror that of the actual lifecycle of the blockchain. If that, of course, makes archival support a lot more complicated, you might have to have either a separate client or you might just say, I don't care about archival support. But I like I've always been fascinated by the idea of a network doing this. And this is definitely something that we want to enable in the Avalanche ecosystem, especially for high performance networks. This is almost a must have to be able to support this. So I'm really interested in having some like bleeding edge subnets that are much more interesting to like add a precompile, even though they aren't necessarily sure, like this might not be the way forever, but this is the way right now. And then be willing to like transition to a new precompile, new type of curve, new verification, and even deprecate the old one. You know, like managing this like tech debt forever is a bad pattern that a lot of blockchains end up having currently. And I think that ends up inhibiting kind of your ability to like push the boundary because you have to be so confident that is actually like the direction you want to go. So I'm really interested in people playing around with this.
Yeah, I mean, I think one of the big changes too, right, with a lot of these precompiles is that it's a smart contract world you don't control, right? This is the double-edged side of permissionless deploys. If you control like the functionality of the chain, you can just remove and deprecate stuff whenever you want because it's not like your execution is going to break because you control the like how it interacts with the network. Okay, you disable functionality, great. As soon as you add an opcode or a precompile to the EVM and someone deploys, or any contract chain for that matter, and you deploy a contract that uses it and then you remove it later, well, that contract now is completely broken. And so if there are if it's called later by anybody, it just won't work. And the worst case is when the changes actually don't remove something, but they change the behavior of it, such that it now makes contracts that expected certain invariants to not even be held anymore. So we're going through a lot of the thinking around this, or like the some of the constraints that we'll need to think about with a lot of the WASM explorations we're doing into programs. But with the Precompile-EVM, it's a little easier to play around with these things than it may be otherwise. Aaron, I think you were going to say something. Or I saw you.
Oh, I think I was gonna talk about Polkadot and the WASM runtime stuff. But yeah, one approach that Polkadot has taken to this problem of, as opposed to just saying we're not going to be able to process historical blocks, is they've actually deployed basically the runtime that's used to execute blocks to the chain itself, so that everyone can use that runtime in order to execute blocks. Which this is a really, really interesting way of doing things because it allows you to perform that update on chain of this is how you actually go ahead and verify future blocks, and it actually gets updated on chain. So even if you haven't necessarily updated your node software, you could actually see that update performed on chain and start using it to verify blocks at some point in the future, which also allows you to just maintain that version of essentially the WASM blob to say we can actually perform these changes and we don't have to worry about processing historical blocks because we'll actually go ahead and use a historical version at a previous point in time. Now, one of the interesting things about this, and I'm guessing the reason Steven keeps looking off in another direction, is there may still be some interesting things where you actually do have to apply it to historical versions, depending on if a particular bug may come up. I don't think this should too frequently be an issue because anything that you process with one WASM blob, you should be able to continue to do so in the future. But it definitely creates a sort of a gray area of like, what is actually the best way to maintain these types of systems? And anytime, if you want to be able to make fluid changes to something, the fact that you will always have to process historical blocks just strictly accumulates more and more tech debt over time. And blockchain systems themselves have only been around for a short period of time, but figuring out how to do this in a sustainable way is very much an art form that's still being developed, I'd say.
I was actually more gonna comment on there are definitely like different approaches that various protocols have taken to try to either like eliminate or reduce this kind of like technical burden. In the Polkadot world, like you do still have to like define like the execution environment that the runtime is running in, right? So like at some point, like, yes, it is like hopefully very general, but if you ever actually need to make changes to the overlying like architecture, then like you still have to like maintain that. Now, hopefully that, you know, if that's not like something that's actually impacting anything on chain, then it doesn't necessarily matter. But like if, for instance, you had a bug not in like the like runtime code, but in like the runtime execution environment, like then you would still have to like maintain that for potentially forever, depending on how you actually, how it's specified. So it's like, you know, depending on how you do this, and of course you could say, well, what if we just put like a straight binary on chain, said execute this, you know, and then it like updates, now you're executing this new thing. It's like, all right, well, now that binary is like going to be like encoded to some like, you know, x86 or ARM, you know, so it's like at some point you have to specify your environment, and like where you make that distinction is very interesting to me.
That's
I
a
don't know.
classic when the bug becomes canonical in a in a way. That's like the funny joke, like with Bitcoin supply is set to 21 million, but the original idea was actually 42 million because like the answer to the universe is 42, but there was actually a bug on the first block that halved it right away by accident. It became 21. So like there's funny, yeah, but nonetheless, I wouldn't say they've decided to reverse that since, but nonetheless.
Sounds like a bullish day one to me.
So yes, I mean, on that note, is there anything, Jay and Aaron, that like you want to see added to the precompile EVM or like cool precompiles you think people should create?
Yeah, I think one that I'd be super interested to see is just, and this I would say is experimental because there's a bunch of things that go along with it, but it'd be really cool to see someone take the stateful precompile that exists now and add support for actually using a WASM blob in order to support the same interface that you could take existing cryptographic libraries that are already implemented in Rust or something else and actually go ahead and use those directly, or even just any Rust cryptographic library over FF5. So there's some example of it. One thing that we've definitely seen is that there's a lot more support for cutting edge cryptography in Rust than there is in Golang. It seems to be catching up a bit now, but it always tails a little bit because there's just a bit less because academics seem to really like Rust and prefer programming in that. So I thought that would be really cool, one easy way to actually support it. And I don't think that the performance necessarily would be too critical out of the box. But that's one thing that I'd love to see.
Yeah, on my side, I think currently the precompiles are more focused on the non-stateful ones, the precompiles I'm seeing. So I think some state support there and like doing crazy things with those like would be interesting.
Yeah, actually, I think that's one thing that the development experience is still not very good for is actually storing variables in the state. As of right now, if anybody's programmed a smart contract in the EVM, what they're probably familiar with is Solidity having storage variables that just appear as if they're any other variables, and you don't really have to think about what's going on to store it in state. But at the underlying level, the EVM is actually only providing storage as a 32 byte to 32 byte map, basically. And so any value that you have that does not fit directly into that is actually non-trivial to fit into that storage. And so Solidity has excellent documentation. Of course, this is all well spec'd out of exactly what the layout of storage variables ought to be within that format. And it can be some along the lines of basically taking the individual slot. It actually depends on the ordering of the variables in your contract. So if you have variables A, B, and C, they will actually get into slots 0, 1, and 2. And so they'll actually go in an ordered format, as well as if you have a dynamic size variable, it'll actually take a hash of that slot and put it into some starting point there, and then add all of the dynamically sized data after that point. But if you're using stateful precompiles, then all that you get is the original 32 byte map And this gives you a lot less to work with. So in our own stateful precompiles, what we've done is we've just assigned individual key value pairs. So essentially there might be a key that says, for all of the allow lists, there is just an address that says like this is the 22 or 20 byte address, and we just insert that directly into this 32 byte map by just 0 extending it in order to store whatever the role of that address should be. But if you wanted to actually treat something even more similarly to a Solidity contract, you might want some additional bindings in order to say, I actually want to declare these storage variables and then use helper functions in order to retrieve their current value. Okay, this is a really cool one. Retrieve their current value or set the value. And so this is actually something that one of the engineers on our DevRel team, Rodrigo Villar, has actually written up a GitHub issue for, and we've had a little bit of a back and forth. But the idea here would ideally be that we can, in the exact same way that we've copied function selectors in order to have precompiles that behave as if they are Solidity smart contracts. What would be really cool as well is if we actually copied the layout of Solidity storage variables as well, so that you could actually deploy your contract using the same sort of API format and declare additionally the storage variables too, and then have bindings in order to access it in the exact same way. And this would be really cool because you could actually go ahead and use this directly. And then even if you were playing around with a stateful precompile, you could use tools that assume that this format exists and works correctly already. And you could actually just look into the storage of the existing stateful precompile, assuming that it adheres to that API and that specification. That's one project that I'm really excited to see. And I think most likely we'll probably not see a ton of actual stateful precompile growth until there's a little bit better support for that. At least not anything that's using very complex states. So like the allow lists are one example where it's trivially easy to just encode like this address is the key, it maps to some value. That's super straightforward to do in the context of the storage that's actually available, but sort of remapping it to this would be an additional really, really cool thing to support and make that development a lot easier, as well as in order to sort of, you could even have some tests that make sure, hey, I have this Solidity contract with these randomly generated variables and set values, and then compare that to the storage that gets generated when you're using an actual EVM smart contract to make sure that everything looks correct and get some pretty high confidence out of that. So I'm super excited to see that go forward.
Are there any, or do you guys know of like any similar tools for something like a lower level, high level language for the EVM, like Viper or something like that, which would be able to more explicitly specify the slots rather, because I just know that like generally like baking something like Solidity into the actual EVM like runtime is generally probably non-standard, and so like I'm interested on if there's like an alternative with a non-Solidity but still like well-supported tool.
So you mean like a different binding of like, this is where this storage variable should go based off of Viper or something like that?
Yeah, like I don't know enough about, like I've literally never used Viper, not a Solidity dev, so I'm talking out of my ass here for sure. But like just like whether or not like rather than having like a Solidity like inspection, we could have like a more like Viper native thing or something that's would allow us to hook into one of these tools without necessarily encoding it into the actual precompile.
So are you saying like you would have a Viper contract that actually runs inside of it, or are you saying you would imitate the storage layout of Viper as opposed to imitating the storage layout of Solidity?
Well, Viper lets you select the storage layout, right? Like I assume that that's something that Viper can let you configure.
Do you mean like from a assembly point of view of like I use this storage slot, or I haven't looked at Viper much either. I mean, you can do like obviously you can do that in Precompile-EVM right now. You can just explicitly put in the storage slot and encode it however you want.
That's what I mean. Like basically, like I'm wondering if there's an integration with a tool that would already exist to be able to inspect existing precompiles that we haven't played around with.
Yeah,
I know like no one. I don't think anyone on this call is necessarily like a huge like Solidity or Viper dev. So I don't necessarily. But I don't know if there's anyone maybe in the chat that would know this. It would be an interesting thing if there's any like good tools out there to inspect the existing like precompiles.
Yeah, I mean, I think
maybe we should have Martin on next time to talk about
yeah, I think either way you have to choose some storage format, and Solidity is the one that generally has more support. I don't think necessarily like Viper being more low level is going to matter too much. Like what we really want is support for the types that somebody might be using in Golang. And at the end of the day, whatever storage format you do choose ends up becoming bound exactly to that precompile implementation. So the idea here would be really just say, yes, I have these variables and it just automatically handles it for me. It doesn't really matter too much what the actual format is, but the ability to actually interact with the existing tooling for Solidity is pretty nice, and I think has better support than for Viper. Would definitely be interested to see if anybody else on the call has some experience with Viper and has some input there, and it definitely is worth looking into. I'll probably send that to Rodrigo if he's not on this call to say, hey, this is an interesting thing to look at as well. Yeah. At the end of the day, the Solidity storage layout is interesting.
So I mean, so for the context, like, so that link I'm sharing is like this cool website called evm.storage. If you haven't seen it yet, pretty cool. This group actually don't know who they are, but they index the storage across a number of different chains that you can just inspect. And so in this case, this is the wrapped Avox contract on Avalanche. And so you can use this to understand a bit about how state is actually mapped here. So for example, like this variable, which has no name but has the value wrapped Avox, is stored at 0x000. Then the value stored at 01 is wrapped Avox. And so the idea here is pretty much like at some point, whatever like smart contract or program usage you're using has to map whatever your understanding of variables is in the code itself or in the bytecode into something that can actually be stored in state. And so the way that Ethereum does this in the EVM is they have different schemes for basically coming up with a single key to represent any particular thing stored in state. And that key is just going to be a hash. And so there's a lot of, you can look up online to see like how like some of your favorite data structures are stored. I think Aaron alluded to some of the difference between static and dynamic types. Like, for example, if you like allocated like a static array of like 100 items, it's going to allocate 0x0 through like 0x100 as the first, range in memory. But if you were to allocate instead like a dynamically sized array, it would instead use the identifier of that array and then randomly put values all over this state of 0 to 2 to 256. So pretty cool to look at. I think, it certainly opened my eyes to some of the like complexity behind the scenes of a lot of these virtual machines and how state is managed. So recommend checking it out, but that's kind of the brief digression on blockchain state here that we're talking about. Yeah.
I just found the documentation for state storage in Viper as well. They seem to do the same thing as Solidity, at least in terms of monotonically increasing the slots that they use. And there's like a brief reference to saying like, and you can also override this explicitly, which in Solidity you can do with assembly as well. It seems to follow the same pattern, but the documentation, it doesn't seem to be as explicit or comprehensive for how it handles dynamic size values. But I would guess that it's doing the exact same thing, to be honest. Yeah.
Well, so I know we're already at 50 minutes in, and I know that Gabriel wanted to chat about a new Postman collection he's been working on for the ANR. So Gabriel, if you want to come back up.
Hey, guys.
I'll share my screen. Yeah.
Thanks. Thank you for having me back. Very, very exciting that the stateful precompiles are coming into focus. It's going to be something which is going to set Avalanche apart. As they mentioned, getting a precompile into Ethereum is very, very challenging. But being able to spin up your own subnet and experiment with this with a precompile is very, very easy and straightforward. So we really feel like that's going to set Avalanche apart, and it's going to empower developers in a big way. And so thanks to all these amazing gentlemen on their work bringing that into focus. So today I wanted to, let me share my screen real quick. Entire screen, here we go. Okay, you should be able to see it soon. Can you see it? Yeah, there we go. Okay, so today I wanted to introduce everybody to the new Postman collection for the Avalanche Network Runner. So very briefly, I just want to bring you back up to speed on what is the Avalanche Network Runner. So the Avalanche Network Runner is a tool that you can use to spin up a local development environment. You can spin up the primary network, so you can have the X, the P, and the C chain, or you can spin up your own subnet. And if you're an Avalanche developer and you're building on the Avalanche network, then this really should be a critical tool in your tool set, and you should really be probably dealing with this every day. Every time you go to develop, you should be spinning up a local network far before even getting to Fuji and much less mainnet. So the Avalanche network is incredibly powerful. It's written in Golang, and you can actually import the repo as a library in your Go program, but we recommend running it as a binary, which you can see here. What's cool about running it as a binary is that you can actually fire up a gRPC server, and the gRPC server basically exposes gRPC API via HTTP. So this makes it very, very straightforward to interact with the Avalanche Network Runner, to add new nodes, to take snapshots, to spin up subnets and blockchains, to really do the full breadth and depth of the functionality via HTTP. So once we started falling down the rabbit hole of this functionality, we realized, hey, we could create a Postman collection for that. Postman is basically some software that allows you to streamline the development workflow of working with APIs like REST APIs and web services. We already have a Postman collection for the AvalancheGo code, and it's been relatively popular. I think the people who use it love it, and we try and turn everybody onto it because, again, if you're dealing with AvalancheGo and you're dealing with HTTP, it's just much nicer to be able to use a nice GUI than to do something like curl request. It scales out better, and you can, share it and work with other people. And so we decided to go ahead and create a Postman collection for the Avalanche Network Runner. So you can see it here. Basically, you would want to clone this repo, and here you see this Avalanche Network Runner Postman file. You would import it here at the top, and then this is going to give you all these collections here on the side. You can see that there's control and there's ping, and then each one of these you can see is like a post request. So you can change the HTTP request here. They're all post. There is a post body, and then you can do environment variables. So we have an Avalanche Network Runner environment variable file. These are different environment variables that you would want to inject into your post requests. So here you can see that I already fired up a server. So we have this gRPC server waiting for commands. And now I'm going to hit it with a post request to start a 5-node network. So a couple of things to pay attention to in this are we're passing subnet EVM as the VM name, and then we have this path to this genesis.json file. So let me go ahead and hit send there. And you can see it's some goodness is happening here in the terminal. And while this is doing its thing, I want to check out what's happening at this path. So this is the genesis.json. So in all instances of the subnet EVM, there's going to be some type of Genesis file that allows you to change the tokenomics, configure precompiles, do that kind of thing. So you can see here in this file, a couple of things to note. We have the chain ID at the top. So this is what you're going to use to connect Core or MetaMask or Truffle or Hardhat, whatever, to the blockchain so that you can interact with it. You can also change the tokenomics. So we have fee config, and we also have alloc. So this is, this particular address is going to be allocated this many gas tokens on block 0. And then there's also, you can see the hello world config. So I was playing around with the stateful precompile hello world that Jay just mentioned in the Precompile-EVM. And then there's also 5 precompiles which come bundled with subnet EVM. For example, the contract deployer allow list allows you to change who can actually deploy a contract on your subnet. Native minter config allows you to actually mint more of your gas token. So for example, if I allocated these tokens to this address and then did not enable the native minter config, then basically we would have a fixed cap asset on this subnet, and that would be all of it that would ever be issued. But if you want to, for example, mint more in the future, you can enable the contract native minter config. There's also a transaction allow list config, which allows you to set who can actually send a transaction on your subnet. We have fee manager config. This allows you to get and set these values at the top. So this, along with the native minter and this next one, the reward manager config would allow you to change the tokenomics. So this allows you to set an address that would get the fees, to continue burning the fees like we do currently, to allow the block producers to get the fees. So this is the JSON file that we used to spin up this subnet. So you can see it takes about 45 seconds, and now we have a 5-node network running, and it gives us this gRPC information that we could then go paste into Core, or paste into MetaMask, or paste into Truffle, or paste into Hardhat, or whatever it is we're using to interface with the blockchain. And then we could go and use the Postman collection to add nodes, remove nodes, create snapshots, create blockchains, create subnets. You can turn a permissionless subnet into an elastic subnet, and then you can add permissionless delegators and permissionless validators. You can print, list subnets, list RPCs. The entire functionality of the Avalanche network runner is now available over Postman collection. So we think that this is going to really empower developers to leverage the Avalanche network runner in new and exciting ways. And I'm interested if anybody comes up with cool workflows to reach out and let me know the stuff you're doing with the Avalanche network runner Postman collection. And it's available now on GitHub. So go check it out, clone it, and let us know what you think. All right. Thank you, gentlemen. Yeah, we're definitely close on time. I don't know if any questions came in. I didn't see any.
I see one I wanted to tackle that was in the YouTube chat. So this one is from, sorry if I'm pronouncing this wrong, Mahath. So in a subnet, can all the subnet validators configure their nodes to state sync, or should there be at least one full node? Great question. So this is something we're actively discussing for a number of reasons right now. To provide some background, right, in a traditional blockchain, the idea is that everyone has all the data from start to finish. So like in Bitcoin, typically, or actually in Bitcoin, definitely, everyone has every block, and when they sync to the network, they re-execute everything that's ever happened. And so if new nodes want to join the network, you can connect to any node and download the blocks. Well, Bitcoin targets a certain throughput to maximize the distribution of the network and the ability to participate. But other networks take a very different position, which is, what if we instead try to push, I don't know, above 50,000 transactions per second? Well, that ends up creating a lot of data, so much data typically that it comes close to saturating a node's network connection. You can get rate limited by your your cloud provider or whatever for actually totally filling the pipe that you're allocated as a node. And so in a world where you're targeting that, it's difficult to even, let's just say you wanted to sync from the beginning, to even do so, because the rate at which you could potentially even sync to catch up is either at or slower than the speed at which blocks are being produced. So long way of saying, even if you had archival on a really high throughput network, you couldn't sync it fast enough to actually catch up to the tip, unless you had some sort of crazy execution thing. But again, the state executions are typically done sequentially. You can't apply a state transition on height 5,000 when you're on height 10, right? There's no, the state that you'd be modifying isn't the right state. So there's been discussion, at least, to start having networks where that's an option, to just disregard old blocks, because if someone wanted to fetch them, it would be useless for actually getting to the tip of the chain. Now, this disregards analysis and validity checking and things like that. But at least for the sake of current validators, if there's never an expectation that someone needs to actually sync the full history, I think it's an open question of whether or not nodes should really maintain it. Now, on the other side, from the Coinbase perspective, for example, they require nodes to actually have, or at least be able to run a node that has full history, so that they can basically audit the balances from Genesis until the current block. So if you don't have any nodes that have the original history, you're kind of between a rock and a hard place, right? Because it's gone. You may have the hash from your earliest block, but no one actually has the data anymore. So there's a huge problem, at least in terms of not data availability in the same way, but data availability in the fact that there's block history that no one can fetch, that you need to reconcile if you do that. So But this is a node by node basis, at least in the way we've defined it. It's not something that like the network can enforce, right? Because it has to do with node runtime. So in a subnet, can you configure their nodes? And the reason why this comes up is related to state sync, which is state sync doesn't actually fetch historical blocks. So generally, our recommendation has been that you should at least have a handful of nodes that have the full history, because it may be required by certain providers. But it becomes a very blurry line as you get into like the super high throughput chains. So I don't know if any of you guys want to add anything to that.
Yeah, I mean, I guess the succinct answer to the question is just like, is it required that there is a validator with the full state? No, as far as the network goes. But like, are there times that that network or the people running that network may find it useful that they have that state? Yes. So, you know, it's up to that subnet, but it's probably recommended to have that state in some form or another. So I think, you know, we've had a number of conversations around perhaps separating out the implementations where you have the current validator, which is validating the current state, and whenever you sync a new validator, you jump into that state and validate from that point forward. And then you have some more like perhaps like scalable data structure based archival structure to support, you know, a horizontally scalable data lake that has all of your archival data. So that's definitely something that, you know, we've been thinking about and playing around with, and I definitely like that kind of mechanism. But
Yeah, great question. Interesting trade-off. No easy answer.
Okay. All right, gentlemen, thank you. We are at time. I want to pass the mic around one last time for last minute thoughts. So Jay, thank you for joining us. Thank you for all your amazing work. Do you have any last minute thoughts?
No, thanks for inviting me here. Thanks.
Awesome. Thank you very much. Aaron, thoughts?
Other than that, thank you guys so much, and thanks to Furkan for taking a look. Also, sorry I forgot that name pronunciation wrong, but thanks so much for taking a look at the Precompile-EVM and building out the velocity curves on there. It's really cool to see.
Thank you, sir. Stephen?
yeah, thanks for inviting me back. Always happy to be here. I've been pushing for all the people on like the protocol/platform team to take a look at that diff validators at diff PR, and I encourage anyone in the audience to look at it as well. I'm very excited to answer any questions, even if you might be concerned that they are like dumb questions. So any question is very welcome to that PR, and hopefully we'll get that merged in the next few days for 1.6. Yeah.
Awesome. Thank you. And Pog, any last minute thoughts?
Not particularly. We're shipping an update to the HyperSDK the next day or so that has a lot of improvements in it, and so it should be cool to see that. And we're just marching towards the first DevNet or public testnet, which we're gonna like denote by Mark. So like Mark 1, Mark 2, Mark 3 testnet's kind of fun. So cool. I'll talk to you guys later. Thanks, Gabriel.
Okay, thank you guys. I'm Gabriel Cardona. You can find me on Twitter at CGCardona. Also, check out Avalanche Developers. That is one single word over at x.com. We will be back in 2 weeks on August the 9th, Wednesday. So get your questions and topics ready and keep up the great work, everybody. See you in 2 weeks. Cheers.
Thanks. Bye.